We will start from Maxwell's equation for matter. We know the Maxwell equation for matter, divergence of d is the displacement vector, which is equal to this, which is equal to 0, and del cross E, which is equal to this, divergence of B is equal to 0, and curl of H, which is equal to this. And further, D, we know this is the displacement vector, epsilon E plus P polarization, B is equal to mu naught H, and J is equal to sigma E, and sigma is the conductivity. To find the wave equation, we consider equation number 2 and taking the curl of this equation. So the curl of this equation is del cross this and del cross this, and further we consider this part in the left side. So this is minus, this should be plus, and putting the value of B mu naught H, and further we can write this can be interchange, uh, del partial divided by partial T del cross H. And what is the value of del cross H? From equation number 4 we can put the value J plus partial D divided by partial T, and then multiply this partial divided by partial T with this and with this, then we can get partial J divided by partial T, and this will be square, partial square D divided by partial T square is equal to 0. And further uh, we can put the value of J here. From here J is equal to sigma E, and the value of D, which is equal to epsilon E plus P. Then if we put the value, then we have this equation, and then multiply this with this and this, then the equation can take the form del cross H mu naught uh, sigma partial E divided by partial T. If we multiply this, then mu naught epsilon naught partial E square divided by partial T plus mu naught partial square P divided by partial T square, which is equal to 0. And here, this is the identity. Uh, if we take the identity, then this identity is equal to del into del dot E minus del dot del E, and del dot del, which is equal to del square, and divergence of E, which is equal to 0, because D is equal to epsilon E, then it also means that divergence of electric field, if there is no charge, then the divergence of E will be equal to 0. Then this term will be equal to 0, and then we have minus del square E plus mu naught sigma partial E divided by partial T. And from here you can see mu naught epsilon naught. So the definition of C, which is equal to, mathematically C is equal to 1 over mu naught epsilon naught under root, and then if we take square, then C square, which is equal to 1 over mu naught epsilon naught, and then mu naught epsilon naught is equal to 1 over C square. So this is the value we have considered. And then mu naught partial square P divided by partial T square, which is equal to 0. The final equation that we have derived. Now, if the field is linearly polarized along x-axis, suppose we have a field which is propagating along the z-axis, then the electric field must be aligned along the x-axis. So if this is z and this is x, so mathematically how we can represent the electric field? So it means that the electric field, it is propagating along the z direction, and this we can write this zt and x. So x you can write, you can represent this by x or I. So it shows the direction of the electric field. So now it means that the wave is propagating along the z direction, but the electric field is along the x direction. This equation can be written minus del square E plus mu naught sigma partial E divided by partial t plus 1 over c square partial E divided by partial t square minus mu naught partial p and t square. And let's say this is in equation number A. We can also consider that this electric field, this is a running wave. Here EZT is a running wave. And having frequency nu, then it means that this electric field must be equal to 1 over 2 epsilon zt. This is the amplitude, and having a phase minus iota nu t minus kz plus phase, and phase is also a function of z and t. Here this is the amplitude and phi is the phase. This is the phase, and both are slowly varying. This is important point. This EZT and phi ZT are slowly varying function, are slowly varying functions, because it depends upon space and time, and it has frequency nu, then k is equal to nu divided by c. So this is, we can write this. If the electric field is a running wave like this, then it means the polarization P of Z and T, this also be equal to 1 over 2 P. This P is different with this. So this is ZT and e की power minus iota nu t minus kz plus phase and zt. So this is the polarization and this is the electric field. Now putting the value of E ZT and P ZT and equation A, and using the approximations. Using these approximations, partial E divided by partial t is very less than nu E. Partial E divided by partial Z is very less than Ke. partial phi divided by partial t is very, very less than nu, and partial phi divided by partial z is very, very less than k, and partial p divided by partial t is very, very less than nu p, and partial p divided by partial z is very, very less than kp. Okay, so now we have this equation A, putting the value of this and this in this equation and using these approximation, then we can get the expression as. Now this is equation number B. First, we will consider the left hand side and then the right hand side, and finally we can compare both, and then we can get some interesting result from this equation B. Initially we will consider the first part of this equation, this part of this equation, and we will try to find the result such as minus partial divided by partial z plus 1 over c partial divided by partial t and e. And what is e? We know the value of e, and e is 1 over 2 epsilon zt, and e की power minus iota nu t minus kz plus phi, and phi is also as a function of space and time, and e is also as a function of space and time. So this is now clear. If I ignore the function of z and time t in my calculation, then it means that this will be a function of space and time. So let's start to solve this equation. We can take minus partial divided by partial z, 1 over 2 epsilon e to the power minus iota. This is a function of z and time, and nu t minus kz plus phi, and phi is also a function of space and time, plus 1 over c and partial divided by partial t, and here 1 over 2 e to the power minus iota nu t minus kz plus phi. Okay. Take the differentiation, because this is a function of space and time and this is also the function of space and time. Then if we take the derivative, then this will be a product rule, minus 1 over 2 partial e divided by partial z and e to the power minus iota nu t minus kz plus phi, and let this is minus 1 over 2 is outside, and plus e to the power minus iota nu t minus kz plus phi, and here this phi is a function of space, so it means partial minus iota. This is also the space and time. This is also a function of space, so it means that minus iota minus k plus partial phi divided by partial z. So this is one part, and the other part is this one. plus 1 over 2c, this is outside, and partial divided by partial, this is also a product rule we can use. Partial e divided by partial t, and e to the power minus iota nu t minus kz plus phi plus e to the power minus iota nu t minus kz plus phi, and take the differentiation of the power, and this will be equal to minus iota nu plus partial phi divided by partial t. Okay, now minus 1 over 2 partial e divided by partial z e to the power minus iota nu t minus kz plus phi, and plus minus, if we take this, then it means that minus iota and minus iota e minus k plus partial phi divided by partial z, and e to the power minus iota nu t minus kz plus phi, and this part is 1 over 2c partial e divided by partial t e to the power minus iota nu t minus kz plus phi, and minus iota e and nu plus partial phi divided by partial t, and e to the power minus iota nu t minus kz plus phi. The previous equations, we can take the exponential term, we can take this common, such as minus 1 over 2 partial e divided by partial z minus 1 over 2 e into iota k minus iota partial phi divided by partial z e to the power minus iota nu t minus kz plus phi. So one part is this, and the other part is 1 over 2c partial e divided by partial t plus 1 over 2c e minus iota nu minus iota partial phi divided by partial t. You can check, this is not very complicated one, minus kz plus phi. Okay. Further, if we apply this, minus 1 over 2 partial e divided by partial z minus 1 over 2 iota e k, this iota e k, and if we multiply this with this, then plus 1 over 2 e iota partial phi divided by partial z, and e to the power minus iota nu t minus kz plus phi, and this term 1 over 2c partial e divided by partial t plus minus this minus iota nu e divided by 2c, and minus iota divided by 2c and partial phi divided by partial t, and e to the power minus iota nu t minus kz plus phi. Now let's use the slowing varying amplitude, the approximation that we have mentioned already in the previous, in the start of this lecture. Partial e divided by partial z is very less than epsilon k, and partial phi divided by partial z is also very less than epsilon. So it means that we can neglect uh, this term and this term, because this is very partial e divided by partial z, this is very less than e, so we can neglect this term and this term as well. And similarly, partial e divided by partial t is very less than nu, and this thing as well. So it means the final terms, we must have this term and this term, this term, this and this and this. This will be neglected using the approximations. So we have the values iota divided by 2 k e and e की power minus iota nu t minus kz plus phi. And from here we have the value minus iota nu e divided by 2c and e की power minus iota nu t minus kz plus phi. Now we can also take common from this and this. If we take common, then we have minus iota divided by 2 k this one and minus iota nu epsilon divided by 2c and e की power minus iota nu t minus kz plus phi. Further, nu divided by c, we have already defined that this is equal to k minus iota divided by 2 k epsilon minus iota, and this is k divided by 2 and e की power minus iota, because nu divided by c is equal to k, nu t minus kz plus phi. And half, it means that iota k minus iota ke and e की power minus iota nu t minus kz plus phi. So this is one part, minus partial divided by partial z plus 1 over c partial divided by partial t e, which is equal to this. Further, this term minus partial divided by partial z plus 1 over c partial divided by partial t e, this can also be written as, if we write this in term of e, then we must have 1 over 2 here, and like this minus 2 iota k and 1 over 2 e e की power minus iota nu t minus kz plus phi. Then this term, we know this term as, because here we divide and multiply this by 2, then this term becomes e. It means that minus 2 iota k e. So this is equal to this one. If we consider this equation b and we find this and we get this value, then we must multiply this with the second term partial divided by partial z plus 1 over c partial divided by partial t, and we get the value minus 2 iota k and e from the left hand side. To solve this further, we must take minus 2 iota k and partial e divided by partial z plus 1 over c partial e divided by partial t. And we know about the value of e, which is like this. Then minus 2 iota k, and partial divided by partial z, 1 over 2 epsilon and e to the power minus iota nu t minus kz plus phi, and plus 1 over c, partial divided by partial t. We have 1 over 2 epsilon e to the power minus iota nu t minus kz plus this one. Clearly, we can solve the same this equation. This is z and this is t. Minus 2 iota k and 1 over 2. This is the product rule. Similarly, we can differentiate this partial e divided by partial z and e to the power minus iota nu t minus kz plus phi, and plus 1 over 2 e to the power minus iota nu t minus kz plus phi, and differentiation of the power with respect to z in minus iota, and we have minus k plus partial phi divided by partial z. And the second term, this one, plus 1 over c, 2c, and partial e divided by partial t e to the power minus iota nu t minus kz plus phi. And the second term is 1 over 2c e to the power minus iota nu t minus kz plus phi, and the differentiation of this power minus iota nu plus partial phi divided by partial t. This one. If we take this term, this term, this term common, then we can write this finally this equation in term of this. Let's see, minus, if we multiply this 2 inside, then 2 will be cancelled out, then minus iota k and partial e divided by partial z, and this term, this can be we can take this outside, and minus iota e, this term, minus k plus partial phi divided by partial z plus 1 over c and partial e divided by partial t minus iota e nu plus partial phi divided by partial t, and e to the power minus iota nu t minus kz plus phi. Now here, one thing it must be noted that we cannot apply the slowly varying approximation here because you know here this k is multiplied with this and this multiply with this and the whole terms. So in the previous case there was no any k, Then if we cannot apply partial e divided by partial z uh, is very less than this e or nu or some other thing, because here we have multiplication k with this term. It means that k partial e divided by partial z is not, it is not possible that this is very less than k or some electric field, this e. So in this case, we can't use the approximation, Schrödinger varying approximation. This is not possible here because there is a k with a multiplication here at the whole terms. The left hand side, we have this term. I will write down. Side, the left hand side of equation B as partial divided by partial z plus 1 over c partial divided by partial t minus partial divided by partial z plus 1 over c partial divided by partial t e. And we have derived this minus iota k partial e divided by partial z minus iota e minus k plus partial phi divided by partial z plus 1 over c and partial e divided by partial t minus iota e nu plus partial phi divided by partial t, and also some exponential term with multiplication exponential term minus iota nu t minus kz plus phi. So this is the left hand side of equation B. Consider the right hand side of equation B. The right hand side of equation B. Minus mu naught sigma partial e divided by partial t minus mu naught partial square p divided by partial t square. And putting the value of e and p here, then we can get minus mu naught sigma partial divided by partial t and the value of e 1 over 2 e to power minus iota nu t minus kz plus phi. This one minus mu naught partial square divided by partial t square and the value of p as 1 over 2 p e to power minus iota nu t minus kz plus phi. So this p, this is a small p, which is also as a function of space and time. This is the same process. We will take the derivative of this because this is a function of space and time and this. So the product rule, and here we will take the double derivative from this. Let's see. From this equation, minus mu naught sigma, if we take the differentiation, then we can get partial e divided by partial t e to power minus iota nu t minus kz plus phi. This is the first term, and then e to power minus iota nu t minus kz plus phi, and the exponential term as minus iota. This is with respect to t, then it means that nu plus partial phi divided by partial t. So this is this term, and the second term is minus mu naught partial divided by partial t, and we can take the one derivative, then this 1 over 2 is outside, then we have partial p divided by partial t, and e to the power minus iota nu t minus kz plus phi, and p e to the power minus iota nu t minus kz plus phi, and this term minus iota nu plus partial phi divided by partial t. So this. Now from here you can take this exponential common, and from here as well, then what you can get, and also you can apply the approximation here. You can apply the approximation partial e divided by partial t as very less than e, and partial phi divided by partial t. You can apply this approximation here. You can apply this approximation, partial phi divided by partial t as very less than nu. So from here you can neglect this term only, and also you can neglect partial e divided by partial t as very less than e, and also you can apply partial p divided by partial t is very less than nu p, and the other one is partial e divided by partial t is very less than nu e. You can use all these approximation here, then it means that this term will be cancelled out and this term will be cancelled out, and here you can also have this term and this term. Finally you can get the result as, after using these approximation, then we have the right hand side minus mu naught sigma divided by 2 minus iota nu e to the power minus iota nu t minus kz plus phi, one term, and from this you can get minus mu naught divided by 2 partial divided by partial t minus iota nu p and e to the power minus iota nu t minus kz plus phi. Now partial divided by partial t, you can again you can apply this differentiation. From here you have u naught nu divided by 2 e to the power minus iota nu t minus kz plus phi, and from here you can get after applying the this differentiation as well, and applying the approximation, differentiation and approximation, then you can get iota mu divided by 2, and here minus iota mu plus partial phi divided by partial t, and e to the power minus iota nu t minus kz plus phi. And here you can use the approximation. This term will also be neglected. Then finally, you can get, I think this is very simple. Uh, you can consider this difference. You can take the differentiation of this and this. This is a product rule, and after applying the approximation, then the partial phi divided by partial t and some other things you have that must be neglected. And then you have the final result, iota mu naught nu divided by 2e and e to the power minus iota nu t minus kz plus phi. And from here, if this you can apply the approximation, then this term will be equal to 0, and then you have this iota square minus, then this is plus nu square, this is p, and mu naught divided by 2 and e to the power minus iota nu t minus kz plus phi. One thing you can do here, mu naught, if you find the value of mu naught, if you, because we know c is equal to 1 over mu naught epsilon naught under root, then c square which is equal to 1 over mu naught epsilon naught, then mu naught which is equal to 1 over c square epsilon naught. Then you can put the value of mu naught which is equal to 1 over c square epsilon naught, then the result must take the form as nu e divided by 2 epsilon naught c square and e to the power minus iota nu t minus kz plus phi. And from here you can also put the value of mu naught, this one, then nu square p divided by 2 c square epsilon naught and e to the power minus iota nu t minus kz plus phi. Now compare the left hand side and the right hand side. This is the left hand side and this is the right hand side of equation B. The left hand side of equation B is this one, minus iota k partial e divided by partial z minus iota. If we multiply this, minus iota minus minus plus iota e k minus iota e partial phi divided by partial z plus 1 over c partial e divided by partial t and minus iota e divided by minus iota nu divided by c and minus iota e partial phi divided by partial t divided by c and e to the power minus iota nu t minus kz plus phi. So this is the left hand side, and the right hand side we have calculated this one. Here nu square divided by c square, we can write this as a k square. Let write and take this exponential term common, then we have iota nu e divided by 2 epsilon naught c square and plus nu square p divided by 2 epsilon naught c square and e to the power minus iota nu t minus kz plus phi. You can cancel out this and this. Further, if we multiply minus iota k with these whole terms, then we can get this term, this term, this term, and which is equal to this. And here, nu divided by c is equal to k. So here, k and c plus here nu square divided by c square, this is equal to k square and p. Now from this equation, separate the real and imaginary parts. So this is e k square, this is a real, minus k e partial phi divided by partial z, and this one minus k epsilon nu divided by c, nu divided by c, this is equal to k, and minus k e divided by c partial phi divided by partial t. And the imaginary part, this is the imaginary part, and this one also is the imaginary part. So plus iota, if I take iota common, then this is equal to minus k partial e divided by partial z, and this term minus k divided by c partial e divided by partial t, which is equal to iota sigma ke divided by 2 epsilon naught. Here sigma 2 epsilon naught, this term sigma 2 epsilon naught c. Let's suppose sigma 2 epsilon naught c, this is equal to kappa. This is a loss term, kappa. Then iota kappa k e and plus k square divided by 2 epsilon naught. And here this p, this is polarization. This has a real and imaginary part. So if I write this, the real part, if I write this real of p plus iota imaginary of p. Now from this equation, compare the real and imaginary part. So this is the real part, which will be equal to the real part here, and the imaginary part. Let write this more simplest form. This is kappa k e plus k square divided by 2 epsilon naught real of p, and plus iota k square divided by 2 epsilon naught imaginary of p. Now compare the real and imaginary parts. So e k square minus k e partial phi divided by partial z minus k e, this is k square, I think this is k square e minus k e divided by c partial phi divided by partial t. This is equal to k square divided by 2 epsilon naught real of p, and the imaginary part minus k partial e divided by partial z minus k divided by c partial E divided by partial t, which is equal to this term kappa ke plus in a more simplified form, we can represent this equation and this equation as I will take this term, and partial phi divided by partial z plus 1 over c partial phi divided by partial t, which is equal to k minus nu divided by c minus 1 over 2 epsilon naught k minus 1 and real of p. You can do this, not more complicated. And partial E divided by partial z plus 1 over c partial E divided by partial t, and this is equal to minus kappa E minus 1 over 2 epsilon naught k and imaginary of p. Now these two equation has a very important consequence. These two equation has very important consequences because here this p, the real part is associated with the phase, and the imaginary part of polarization is associated with the amplitude. So it should be remembered that polarization is directly related to the refractive index of a medium, and the refractive index of the medium is directly related to the susceptibility of the medium. So if we consider the susceptibility of the medium, and we say that the susceptibility has two parts. One is the real part and the other one is the imaginary part. And usually you can see that the real part gives us the dispersion property, and the imaginary part gives us the loss or gain property, because the polarization is directly related to the susceptibility. Now here the real part of this polarization is directly related to the phase. So if you take the dispersion, so the dispersion means you can directly relate to the phase. So here you can see that this is related to the dispersion and this related to the absorption, and it is because that the real part of the polarization is directly related to the phase, and the imaginary part of the polarization is directly related to the amplitude. So this is related to dispersion and absorption.